Good afternoon, everyone. In the last class, just we started the integrated rate equations, right? And that zero order reaction. Now we will continue here. The further the zero order reactions. Or zero order kinetics. Which we can recall the yesterday's formulas. That is, at time t, the concentration of the reactant is A0 minus Kt. This is one formula we have, and the concentration of product at time t is equals to x equal to Kt. And these are the two formulas, and this is with respect to reactant concentration, and this is the product concentration. Next we have one more formula, that is off life. Off life is equals to initial concentration by 2K. These are the things we have discussed in the last class. Next we will see now here the characteristic properties of first zero order reactions. Some of the important points or some characteristics. The main characteristics here, anyhow we know that rate of the reaction is independent on the concentration of reactant and time, and off life of the reaction is directly proportional to the initial concentration. And apart from this, when equal concentrations of a reactant reacts, we can take this statement, equal concentrations of a reactant reacts is reacts in equal time intervals. This is equal concentrations of reactant reacts in equal time period. So what it means actually, equal concentrations of reactant reacts in equal time period means what? Let us take, initially we have 100% of the reactant. Let us assume to convert some amount, almost 10 concentration, let us assume it requires 5 minutes. Then it left with 90. Equal amount is 100, in that the 10 is decomposed and 90 left. Again from 90 to 80, the initial concentration, again decompose amount of 10, and again 80 to 70 or 70 to 60 and so on. So here to convert 100 to 90, if the time required is 5 minutes, again to convert 90 to 80, again the time required is the same, that is 5 minutes. Again 80 to 70, again the time required is 5 minutes. This is for zero order reaction. That means equal concentrations of reactant. Here how much is reacted? 10, and here again 10, and here again 10, here again 10. So equal concentrations of reactant react is in equal time period. So here if it is a 5 minutes, here also 5 minutes, here also 5 minutes. That is the characteristics of zero order reaction. So one more here. Concentration of reactant remaining. Concentration of reactant remaining after equal time period. Form an arithmetic progression AP. Means what? Let us take previous. Here 100 to 90, 90 to 80, 80 to 70, 70 to 60. Concentrations of reactant remaining after equal time period. So here 5 minutes, 5 minutes, 5 minutes, 5 minutes. Here left 90, here left 80, and here left 70 and 60, so on. And they can form an arithmetic means, and they are having the common difference. This also we can explain. Let us assume we have the formula amount of reactant remaining at time t is equals to A0 minus KT, and this is the formula we have. So initially let us assume at a time t equal to 0 we have A0, and at a time t equal to t then we have A0 minus KT, and at a time 2t we have the formula A0 minus 2 KT, and at a time 3t now A0 minus 3 KT, and so on. Now we can see the difference here, the common difference A0, A0 minus KT, the difference is KT. Again here the difference is KT, and again the difference is KT. So hence it can form the arithmetic progression according to the mathematics. Right. These are the main characteristic properties. So concentrations of the reactant remaining after equal time periods. Here to here the time period t, and here to here again t, and here to here again the t. Okay, that is something about the zero order reactions. So one more important point about the zero order reaction. Let us take one reaction with some coefficient n. Let me take Na gives rise to products. Again let us assume it is a zero order reaction. Then in this particular case, again what is the reactant at a time t, and what is the product concentration, and what is the half-life? How can we write here? Previously we have taken that A gives rise to product. So your stoichiometric coefficient is 1, but if you change the stoichiometric coefficient, so will you observe any change with respect to the amount of reactant left, or amount of product to form, or half-life? So then you will get the formulas. If this is the case, we have one formula previously, reaction constant, that is a rate constant formula. A rate constant of reactant is equals to a rate constant of reaction into its stoichiometric coefficient. Isn't it? By using this, now you can write concentration of A at a time t is equals to A0 minus, in place of K. Now here with respect to A we are studying, so with respect to A means reactant of K, a rate constant of reactant. Rate constant of reactant is equals to K into stoichiometric coefficient. Then what is the stoichiometric coefficient here? N into K, that is a reaction rate constant, as usual K into T. So you can use this formula. If they give the stoichiometric coefficient, this is the formula. Then X, amount of product. So with respect to product, there is no effect on the stoichiometry. Directly you can take X is equals to KT. And again if you take half-life of reactant is equals to, that is A0 by 2K. Again K means in place of K you write NK. So these are the some modified formulas when we take the stoichiometric coefficient. Just remember these two formulas, half-life and amount of reactant left. Now let us take few examples related to this. For example, we have 3A forming product. It is a zero order reaction. Then concentration of A at a time t is equals to, you can write, that is initial concentration minus the stoichiometric coefficient now 3. So 3 kT, like this you can write. If you go with off life, T off is equals to initial concentration A0, 2 into here stoichiometric coefficient 3, 3K. That means A0 by 6K. And if you take the stoichiometric coefficient in different manner, for example, if you take 5 by 2A, gives rise to product. Here again you can write AT is equals to A0 minus 5 by 2 KT. Just in place of K we have to write NK. Again off life is equals to A0 by 2 into 5 by 2 K. So overall you get 2 will cancel, you will get A0 by 5K. And this is the off life for this reaction. For example, if I take 2 reactants involved, one more, like A plus 2B gives rise to product. Again zero order reaction. Again if you want to calculate the amount of reactant left, there is a reactant A and reactant B. Now we have 2 reactants, and with respect to AT we can write the formula A0 minus KT. This is okay with respect to A, but if they ask with respect to B, then amount of B left after some time T is equals to, we have to take initial concentration of B minus, now you have to take its B stoichiometric coefficient, that is 2 KT. And similarly off lives, if you want to talk, T off is equals to A0 by 2K, but in this case T off for reactant B, and there is a reactant A and this is a reactant B, is equals to B0 by 2 into 2K. This is all. So if they give individually 2 or more reactants or 1 reactant, whatever the stoichiometric coefficient, just you multiply that one. Okay, now we will see a few examples related to the zero order reactions. A few questions. Rate constant of a reaction A gives rise to product is 2 into 10 power minus 2 molar second inverse. After 25 seconds, concentration of reactant remaining is 0.5 molar. Calculate initial concentration of reactant. What is the initial concentration of reactant? So what they gave here, rate constant is given, and at a time t, the amount of concentration, direct the formula. What formula we have? AT is equals to A0 minus KT. From this we have to calculate initial concentration, means A0, that is equals to AT plus K. It is given 0.5 and into plus 0.5 plus 2 into 10 power minus 2 into 25. How much you will get? 0.5, 0.5, 1 molar. We will take A gives rise to product. Initial concentration of reactant is 0.01 molar. After 10 minutes, concentration of reactant remaining is 0.008 molar. Then calculate half life. Calculate half life. So simple, the solution for this. So they are asking half life, anyhow zero order reaction, T of equal to A naught by 2K. Initial concentration is given already, that is 0.01 by 2K. We required the rate constant K. Now what formula we have? Rate constant K is equals to A0 minus AT by T. Initial A0 0.01 and final concentration 0.008. At what time? The time interval of 10 minutes. And that can give 0.002 and this one 10, 0.002 molar minute inverse. So here it is, the time is minute. Why? Because we are taking here 10 minute. So this K value substitute here. Like 0.01 by 2 into 0.0002. So it will give 25 minute inverse. If you convert further into seconds, you multiply with 60, you will get 1500 seconds. Like one more last question here. For a zero order reaction, calculate the time for the following conversion. Just like it is given like this. This is how much. Simple logical based question. See what it means, the four objects or some four particles, they are converting into the one particle. So nothing but this is T75%. Out of 4, 3 consumed and 1 left. So 75% of the reaction is completed. And this one, out of 4, 2 are consumed and 2 left. Means this is a T50%. Anyhow, this is a zero order reaction. For zero order reaction, T50% is equals to, this is 1.5, means T75%. 2 by 3 times of T75%. Actually we have T75% is equal to 3 by 2 times of T50%. So 2 by 3 into 3 can give 2 seconds.